Tucked away in the English Channel, the island of Jersey is a landscape defined by its relationship with the sea. On June 25th, temperatures across this island hit 39.3 degrees Celsius, or nearly 103 degrees Fahrenheit. That measurement broke a local climate record that had remained a baseline for Jersey since 1894. Public response to these peaks typically focuses on immediate human comfort, finding shade, increasing hydration, or seeking air conditioning to survive the hottest hours. Examining the environment as a vertical cross-section reveals a more complex interaction. An extreme heat event functions as a structural pressure applied across four overlapping layers: the atmosphere, the night sky, the surrounding ocean, and the soil below. The Jersey data suggests that focusing only on daytime air temperature overlooks how heat physically alters the entire vertical stack of a local environment simultaneously. The atmospheric impact in Jersey was defined by its duration. Between June 21st and 25th, the island experienced 4 consecutive days where daytime temperatures exceeded 30 degrees Celsius. This sustained thermal radiation places a direct physical strain on the surface environment. Soils lose moisture rapidly, and vegetation reaches its biological limit for processing heat. In a typical cycle, local flora and fauna rely on the sunset to begin a recovery process. This drop in temperature provides a necessary window for organisms to release stored heat and stabilize before the sun rises again. During this heat wave, Jersey recorded 3 consecutive tropical nights. These are periods where the temperature fails to drop below 20 degrees Celsius, meaning the environment never reaches its cooling threshold. That sustained elevation on the chart represents a total loss of the biological recovery window. Because the heat is never fully released, the ecosystem begins each subsequent day with a higher internal temperature, making each 24-hour cycle more damaging than the one before it. By maintaining these high temperatures after dark, the heat wave converts the night from a period of rest into a period of cumulative environmental stress. Beyond the air and the night sky, the heat penetrates the surrounding water. For an island environment, the ocean usually serves as a massive thermal regulator, absorbing heat and cooling the land. That regulatory effect weakened in June as the average sea temperature rose to 16.2 degrees Celsius. For context, the coldest June sea temperature on record for the island was 13.5 degrees, recorded in 1986. This warming of the coastal waters reduces the ocean's ability to provide a cooling buffer, while simultaneously exposing the marine ecosystem to higher thermal loads. Below the surface, the island's hydrological layer faced a different kind of pressure. The month's rainfall was distributed in a way that left the land vulnerable just as the heat arrived. Although Jersey received 49.1 millimeters of rain in June, 44% of that total fell on the very first day of the month. By the time the heat spike began 3 weeks later, the soil was already parched. This historical image captures the physical result of rapid soil evaporation. During the June heat spike, the combination of dry soil and high temperatures pushed water demand on the island to its highest level since the drought of 2022. With the ocean no longer providing its typical cooling effect and the land stripped of its moisture, these environmental systems begin feeding into one another, compounding the total stress on the island. The data from Jersey shows the multi-front nature of a modern heat wave: high-intensity air temperatures, elevated nights, warming oceans, and dry land. This timeline shows how the frequency of these events is changing. While it took over a century to surpass the 1894 record, the new June peak comes just 2 years after a previous record-shattering event in July 2022. These environmental shocks are occurring with higher frequency, rapidly adjusting the local climate baseline toward these higher extremes. Addressing this shift requires moving away from the idea that extreme heat is a temporary weather inconvenience to be managed with individual cooling. Resilience in this new era requires a structural response to protect the island's resources, from managing municipal water levels to adapting agricultural practices for a drier landscape. Protecting the environment now means defending every layer of the ecosystem, because when the heat arrives, no part of the landscape is untouched.